Welcome everyone, I am Keitana and in this tutorial we talk about Gpgpu programming with Cuda. First we'll see what is Gpgpu. General Purpose Graphic Processing Unit is a graphic processing unit. It means Gpgpu is a GPU. Yes, we all knew something about GPUs, that the GPUs to be a graphic card that the gamers need for video games. But the GPU does much more than just graphic processing. Initially, the main purpose of the GPU was to render 3D games. It's to generate a realistic photo image from a 3D model. Over time, this component evolved to become a GPU with general purpose. So all modern GPUs are considered to be GPUs because they can be used not only for graphics but also to run calculations and perform tasks. Now, do we remember what is GPU and how it's work? A GPU is a microprocessor. It does specific tasks like quick mathematical calculation to manipulate and display the images on the computer. GPUs are composed of memory, capacitors, voltage regulators, power supplies and other components that some of us like to manipulate. A GPU has everything needed to be programmable. So what's the difference with CPU? CPU can sequentially execute the process with multi-cores and must wait for it to finish in order to start a new one. But a GPU has thousands of cores that are capable of performing thousands of mathematical operations in parallel. That's why a GPU is a very powerful computational device. Building on the idea of parallel processing, for example, breaking up the processor into smaller bits and sharing the process between the cores, we can get more done in shorter period. Since a single GPU can perform calculations at much higher rate than a CPU. Sharing multiple GPUs together exponentially increase the computational performance. It is a much more common practice to integrate multiple GPUs in a system rather than multiple CPUs. There are several types of GPU, although GPUs usually operate at much lower clock speed than a traditional CPUs. A GPU has massive amount of cores that help with multitasking. The Gpgpu allows the developers to create and port their programs to use the GPU for an increase in performance. Easy integrations and high efficiency are two of the ways Gpgpus differ from traditional CPUs. Now let's see what kind of problems are suitable for Gpgpu. If your code involves lots of large loops, especially nested loop, in such case consider using Gpgpu. If the code within the loops can be reduced to a fairly simple algorithm, it is a good candidate. If your dataset fits or can be made to fit into the memory of the hardware, it is a very good candidate. If your code involves manipulating large matrices, Gpgpu should be ideal. To get best result, you will have to do some fairly low-level C programming. For all hardware, you will need both a device driver and a development framework. There are two frameworks in general use. One is Cuda and other one is Open Computing Language. Now let's see what is Cuda. Cuda is NVIDIA's property framework. Cuda stands for Compute Unified Device Architecture. It is a parallel computing platform that gives developers the tool they need to utilize many cores on a GPU. It is mature and runs C, C++ and Fortran code natively. And the third-party wrappers are available for language including Python, Perl, Fortran, Java, and etc. There are multiple versions and each in its own directory. GPUs were once very difficult to program, but developers can now use standard programming language of today, such as C to accomplish this task. Cuda is what allows NVIDIA to take the GPU to the next level and go beyond the traditional means of graphics rendering. Cuda is now a big deal in the industry, and whenever NVIDIA releases a new graphic card, they explicitly list out the number of CUDA cores it has. To some degree, the more cores a GPU has, the more efficiently it can handle the parallel processing. Since GPUs require the ability to provide for more calculations and computation, it is essential to have a higher number of CUDA cores for a performance reason. The benefits of GPUs are, if you work with lots of photos or videos, a fast GPU is good for editing software, says Antoinette St. Slow, who oversees the computer testing at Consumer Report. Tasks that take a long time on an integrated graphic chip can run much faster on dedicated graphics. And plenty of well-known editing software applications take advantages of added oomph of GPU, including Adobe Photoshop for serious photo editing, Lightroom for more lightweight photo editing, as well as photo library management, and Premiere Pro for editing and rendering the video. On a computer with a powerful GPU, it takes significantly less time to apply complex filters to the photos and special effects to the videos. That means less time waiting and more time creating. You will also see improved performance when running these apps on higher resolution screens. Now let's have a discussion on Cuda example with the help of Google Colab online service. Google Colab is a free cloud service and it's offer GPU and it's completely free. With Colab, we can work on the GPU with Cuda C++ for free. In order to run our code, we need to do some steps. First, click on New Notebook, and then we need to switch our runtime to GPU. To do that, click on Runtime here, and then click on Change Runtime Time. Here, change the hardware accelerator to GPU. Then save. Now, okay. Now we need to uninstall any previous CUDA version. We need to refresh the cloud instance of CUDA. To do that, we need to run this code. Here, the exclamation mark is in the first line. Every line starts with exclamation mark. It will be executed as a command line command. Let's run the code. It will take some time. So now uninstalling the previous CUDA version is finished. So now I am going to install the CUDA version 9. To do that, click click on the separate code block, and here I need to run the installation part. Now the installation is finished. Let's check whether the installation, CUDA version 9 installation is success or not. To do that, we need to run this code. Yes, it's successfully installed. So now we need to install a small extension to run NVCC from the notebook set. To do that, we need to run this code. It's finished. And now we need to load the extension using this code. Let's run this code. Yes, now it's ready to run our program. I am going to do a simple Cuda example for adding two numbers. There are some sequence of operations for Cuda C program. First one is define a kernel. It's a function to run on the GPU. Then the second one is allocate and initialize the cost data. And the third one is allocate and initialize the device data. And the fourth one is invoke a kernel in the GPU. And the fifth one is copy the kernel output to the cost. And the sixth one is clean up. So now it's ready to code, and I am going to code for a simple calculation. Before that, to run our code in this notebook, we need to add an extension at the beginning of our code. This extension. Now we can code. We can start our coding. So I'm going to add two number coding. In here, this keyword global to define a kernel. We use this keyword global to define a kernel. A kernel is a function to be run on a GPU instead of CPU. This kernel adds two numbers A and B and store the result in C. Now we allocate and initialize the cost data. Here I will allocate and initialize the cost data. In the cost, allocate the input and output parameters for the kernel call and initiate all input parameters. Now, allocate and copy the cost data to the device. A Cuda application manage the device space memory through the calls to the Cuda runtime. This include device memory allocation and delo allocation, as well as the data transfer between the cost and device memory. We allocate a space in the device, so we can copy the input of the kernel A and B from the cost of the device. We also allocate a space to copy the result from the device to the cost later. After this, we invoke the kernel. To invoke the kernel, we need to add this code. To provide the data parallelism, a multi-thread Cuda application is versionated into the block of thread that execute independently from each other. Each parallel invocations of is referred to as a block. Each block have multiple threads. These block of threads can be scheduled on any of the available streaming multiprocessor within a GPU. In our simple example, since we just add one pair of numbers, we only need one block containing one thread. Now we copy the kernel output to the cost. This is the code which copy the kernel output to the cost. Then we clean up the memory. Have to print my answer, oh, so then only I can check whether my coding is running. Here I am adding A plus B and the result is served in C. Here A is equal to 1 and B is equal to 0. So the answer should come as 1. Let's check our answer by running. The answer is 1. So that's all.